So what determines which type of dune will form? Also, the relative strength of winds from different directions. For example, is there one main wind direction or are there several? And finally, how much do those wind directions differ from each other? And whether vegetation, ice, and so on anchor parts of the dune in place, as in the parabolic dunes. And there's more that we haven't even talked about, like the size of the sand grains, for example. So there are lots of other more complex dune types, but let's review the main ones we've talked about. So what determines which type of dune will form? Well, if we have wind coming from one direction, what kind of dune type do you think will form? If you have limited sand, then we tend to expect a barchan dune. If you have unlimited sand, we expect to see transverse dunes. So with a gentle side here on the Stoss slope, and then a rapid drop here on the slip face on the lee side of the dune. Or if we're anchored, if part of the dune is anchored by vegetation or moisture, you might have a parabolic dune, where again the slip face is the opposite side to the incoming wind direction, but now you've got these horns being anchored here and the middle of the dune being blown outwards. How about if you have wind from lots of different directions? What do we expect then? Well, we might expect to see star dunes, or perhaps complex network dunes. And what if we have winds from a couple of directions? Well, then we probably expect to see longitudinal dunes. And in this case, both faces of the dune, both sides of the dune, are going to be roughly having an equal slope to each other. But that's not always what we see. What dunes form when there are two dominant wind directions can depend on their relative strength, the angle between them, and how much sand there is. So scientists have run lab experiments and computer models to simulate how dunes form in different winds. And this is an example of a lab setup where you basically have wind that's always coming from one direction in the lab setup, but you have a dune field, a big sand pile here, and you rotate the sand pile. So it simulates being able to have wind from multiple directions. So you might have it here to start with, so the wind is coming from this direction, and then you rotate it around so that the wind is coming relative to the sand pile from this direction. So you can vary the angle and also the strength of the wind coming from different directions. And this is done underwater. So it's really water flowing over the dunes rather than air. So if we have a 30-degree separation between the two wind directions and we have equal amounts of wind from each direction, then we get something like this, which looks very like transverse dunes. However, if we then change the angle between the winds to 90 degrees, well, then we get this kind of mixture. Sometimes it looks transverse, sometimes it looks more longitudinal. And then finally, if we have winds separated by 120 degrees, we now have dunes in this particular case that look like they are longitudinal. And this is a computer model of dunes that will form if lots of sand is available for different angles between winds and different relative wind strengths. So you can see that if we have a 30-degree angle between the two different wind directions, then no matter what the relative speed is of those two winds, the strength of the two winds, you basically get transverse dunes in all of these cases. However, if we increase the angle between the winds, then you get kind of transverse dunes with superimposed transverse dunes. So you get transverse dunes predominantly from this strongest wind direction, but then some superimposed dunes that are much smaller, and they're sort of on top of it, that are transverse in this direction. But when these two winds have pretty much equal strength, then we end up with longitudinal dunes, where the dunes are very clearly parallel to the mean wind direction, to the average wind direction. And then when we go even further to a much higher angle between winds, we then get transverse dunes with superimposed transverse dunes, something that's sort of in between here. And then over here we get longitudinal dunes. Now, if we take pretty much the same angles and the same relative wind strengths, but now we say, well, what happens if we only had a little bit of sand available? Well, now we get Barkhan dunes for the 30-degree angle. We get Barkhan dunes or Barkhanoid dunes, so kind of curvy, but maybe starting to elongate into longitudinal for the larger angles for one of those wind speeds dominating. But when we have equal wind speeds from the two directions and a slightly bigger angle in both those cases, and in the intermediate wind speed case for the smaller angle, we very clearly get a longitudinal dune, which is basically just that sand pile elongating in the average direction of the sand transport. So Venus has a very thick atmosphere and high surface pressure. Winds can reach 220 miles per hour high up in the atmosphere, but they actually reach less than 10 miles per hour at the surface, so pretty sluggish, really. These low winds and Venus's high surface pressure can suppress siltation and hence dunes, although some dunes and dune fills have been identified. So here are some dune fills that have been seen in Venus radar data taken from orbit by the Magellan spacecraft. And recently, scientists have been looking at underwater dunes on Earth, where the pressure is also very large, as an analogue for dunes on Venus. And the idea is that when you have very high surface pressure, it's harder for those sand particles to bounce up and down and siltate and create dunes. New Horizons spacecraft took some flyby images of Pluto that also showed dunes, and that's despite Pluto having a very, very thin atmosphere. And so if we zoom in on this image, we can see what look like maybe longitudinal dunes here. And they could be formed by sand-sized grains of solid methane ice that are transported in typical Pluto winds. And then finally, this shows a Rosetta spacecraft image of the surface of a comet. And this is so amazing. There actually are ripples on the surface of a comet. So it shows an image of ripples taken after the comet's closest approach. But the position of them in another image, which was taken 2 years earlier, so before the comet's closest approach to the sun, are superimposed in yellow. And the fact that the ripple positions have moved between these two images, even though the rest of it, the rest of these rocks have stayed in the same place, indicates that these ripples are active, that they moved, that some wind moved them over this period of time. So what scientists think happened is that as the comet neared the sun and ice evaporated from its surface, this gas and the strong day-night heating differences caused winds that moved the surface grains. And the grains lightly moved in a process called traction. That means they stayed on the surface instead of hopping the way that siltating sand does. And I just want to show you this amazing images from the probe from Rosetta Philae that landed on the surface of the comet. And unfortunately, it did bounce a few times after landing, and it ended up in a dark crack in the surface. So they finally managed to track where it was at different times. You can just see it in this image. It's really amazing that it actually managed to sort of survive. And then here it is where it ended in this dark crack. But it still sent back the first images and other data from the surface of a comet. So this clip is made up of 25 minutes worth of images from the lander processed by someone on Twitter. And this snowstorm effect looks very cool and dramatic, but it's really probably due to moving dust particles backlit by the sun, cosmic rays, and or stars. And stars are these things that appear to be moving straight down And that's because this comet is actually rotating, so it's moving relative to the star field. And so it looks like there's a lot of snow going around there, but really all of this is not really snow.